first welcome everyone to join the Professor Morton's seminar, and I'm just going to briefly introduce Professor Morton. So today, it's our great pleasure to invite to have Professor Morton to give this seminar, and this is really it's our privilege and to have Professor Morton. So Professor Morton is Helena Hilbert Craft Professor in the N and H.J. Smith Aerospace Engineering Science Department at University of Colorado Boulder, and her research expertise lies at the intersection of satellite navigation technology, so GNSS, and remote sensing of ionosphere, troposphere, and Earth's surface. So, and Professor Morton received her PhD in electrical engineering from Penn State, and she's a recipient of AGU Spark Award, IEEE Richard Kirschner Award, and Institute of Navigation, the Burkhardt, Navigation, the Burkhardt Third Load, and Distinguished Service and the Kepler Award. Okay, so everyone can see it's amazing this experience and all the numerous awards. And Professor Morton is a fellow of IEEE, the Institute of Navigation, and the UK's Royal Institute of Navigation. So so just a few things I would like to add on is that we have this honor to have Professor Morton visit and attend this ICGPSR meeting under Tasty the last year. And that time, the Professor Morton gave this wonderful presentation about all her application of GNSS reflectometry. And that's the first time that I'm the meteorologist, the scientist. But that's the first time that I know Professor Morton's work, and it's really amazing and open our eyes for all kinds of different application for the GNSS reflectometry. So as you know, last year we have very successful launched for Triton mission. So now we are really looking forward to how we can really bring up the value of all this data, the importance in scientific research, and in particular, not only for the atmosphere science, but also for Earth's surface and all kinds of application. So it's our great opportunity that we can learn from Professor Morton today. So let's welcome her, and thank you very much. Okay.
And thank you so much for your introduction. I think there must be a little bit of communication issues when I was asked to give a talk, and I thought I was asked to give a more general topic, but don't worry. The talk will be mostly focused on reflectometry, but the title I'm having here is GNSS as Signals of Opportunity for ionosphere, atmosphere, and Earth surface remote sensing. But I made most of the talk focused on reflectometry because it's one of the most exciting areas of research that my lab has been working on. And I would like to just open up with a little bit of background for those of my colleagues here who are not familiar with my lab. And my lab is called Satellite Navigation and Sensing at the University of Colorado. Let me do this hide. Oops, I think. Okay, here it is. And so what we're focused in are mostly, I call them the last 5% of the journey of the signals that's transmitted by GNSS satellite. I'm going to put laser pointer here. And so, and that start at the ionosphere, about 1,000 kilometers above the Earth's surface. The ionosphere plasma interact with GNSS signals, causing delays and interference on the signals. That's one area we're focused in. The second area is the troposphere, in particular water vapor. It impacts the weather systems and also scatters GNSS signals, making it difficult for receivers to operate. And further down the ground, there are grasses, trees, especially in Taiwan, all this lush rainforest. It's beautiful, but it can hamper GNSS signals, propagation. And of course, buildings reflect the signals. Multipath reflection is a big problem. So these are all the things that people design GPS navigation receivers they don't like them because they are nuisances. And of course, there are also interferences. And but I like them because they are ways for us to understand what is happening to the signals and what is happening in the environment. So these are nuisance factors for navigators, but for remote sensing people, these made GNSS signals are signals of opportunity. And of course, we don't just have receivers on the Earth's surface. We also have them on radio occultation platforms. And Taiwan is a major contributor to radio occultation systems with the Formosa series of satellites, and that really advanced GNSS research for scientific applications. Now, lately, a lot of focus has been on GNSS reflectometries, where an antenna on a satellite in LEO orbit could be mounted downward, sideward direction that can pick up signals that are reflected from Earth's surface that allow us to sense surface properties. So these are all the things that we're interested in. And if we wanted to summarize in scientific terms, what are the kind of effects our environment can have on GNSS signals, I would summarize in these 5 terms. So our environmental factors can absorb signals, it can make signal band, it could delay propagation, and could reflect signals or scatter signals. And now, why we're really interested in GNSS? There are many radio signals out there. Why GNSS is in particular advantageous for these kind of applications? That's because the signals are free. Someone else is transmitting them. They're already up there. There are large numbers, several hundred of them in space, and optimized, distributed around the world in such a way that they are global coverage. And another important advantage is it is well defined. We know exactly what the modulation is, what the center frequency is, what data messages are on there. So any kind of disturbance on it can help us understand what the environment has did to it. And finally, there's enough diversity. The signals are spread over the L band from 1.1 to 1.6 gigahertz and have different bandwidths, different modulations that allow us to look into the kind of environmental impact from multiple perspectives. So those are advantages, but they're challenges. And the signals are very weak. This is typo here. And the signal can be discontinuous. I missed the D here. And so that causes trouble as well. And we also have to be able to distinguish the effects from platform, like the receiver may be moving on some platforms. The platform may have problem. They may have vibration or other things. How do we distinguish those effects from environmental propagation effect? And the GNSS signals are all narrowband signals. Narrowband signals have its own challenges. That's another thing we'll have to address. And there are all sorts of interferences, both intentional and unintentional, that could also further impact our effort in understanding our environmental factors. So these are the challenges. And so in my lab, we divide our research into 4 areas. The first area is deploying global network receivers so that we can monitor the signals. The second area is taking the data that we have acquired over the years, as well as data from other systems and other people's network, to monitor the ionosphere, to develop machine learning algorithms to forecast the space weather. The third area is GNSS reflectometry, and I'll get into a lot more details in there. And the last area is developing navigation technologies so that our CubeSat can work better in space, and they can have a better orbit determination. We can navigate better in urban environment, and we can mitigate effect from the ionosphere and the troposphere, so we can have a better solutions. And those better solutions not only enable better navigation technology, but enable better remote sensing technology development, like the kind of topic we're interested in here. So the kind of subject we're really interested in are the ionosphere effect, troposphere, multipath reflections, ground foliage, including trees, and indoor urban environment, and how do we mitigate interference. All of these are related. If we wanted to study ionosphere and troposphere, how can we distinguish those effects are actually from ionosphere, not from man-made interference, and not from multipath? So these topics are not isolated. They are related to each other. That is why we have to study them all of them in a holistic way. And of course, we want to be able to study them from various perspectives. And with sensors mounted on aircraft, low Earth orbiting satellite, like what the Triton is doing, UAVs, and from ground. And there are two distinctive arms that we're interested in. One side of the arm is sensing and situation awareness, where we want to be able to characterize all of these factors that are shown up here, the ionosphere and troposphere and all those, want to be able to characterize them, model them, and from the sensing and situation awareness perspective, that allow us to retrieve information about our environment. The second arm, the other side of arm, is developing PNT, which is a position navigation timing technologies, under challenging conditions. The challenging conditions are due to all of those sources, the ionosphere, troposphere, multipaths, the things are listed up there. And what we're interested in, understanding their impact on navigation receivers, and then allow us to develop mitigation techniques so that we can make the receivers work better. And so really, all of this, I would like to unify them under one platform, that is GNSS receivers. If we don't have good receivers, we're not going to be able to get the kind of signals to retrieve the kind of scientific information that we wanted. And so my labs really focus on GNSS receivers. And in particular, we address these challenges are listed in the last slides. How do you work with very weak signals? How do you handle measurement discontinuities? How do you separate the platform and the propagation effects? How do you overcome the limitations for bandwidth of narrowband? And how do you make sure you're not classifying or treating man-made radio frequency interference as scientific signatures? So those are the things we're addressing, and to enable the kind of applications to allow us to monitor space weather and to map atmospheric water vapor and to study ocean, sea ice, land ice, and the soil, rivers, and the lakes, and also finally to enable robust navigation technology. So this is, if anybody's going to ask me, what do you do? This is the slides I would present. And the reason I want to present it here today is that so everybody understand where do I come from? I come from GNSS receivers, and we're receiver expert, and our particular capability is handling those signals that most people want to throw away, and we like them, and we want to work with them to enable the kind of applications that's beyond what GNSS was designed for. And feel free to ask me questions anytime. And I couldn't see people raising hand or putting messaging in the chat boxes, but just to speak out. And you might ask, how bad can things go, and what kind of extreme conditions your receiver can work with? I'm going to just show you one slide. So this is slides over 3 hours, and data that we collected an island over the Atlantic Ocean. And so this is from a GPS satellite, a GPS PIM-25. And the reason I want to show you is that if you look at the blue lines, you can see they're over 2 hours period. The most advanced GNSS receivers will lose loss log, couldn't work with it. And so we bought a $25,000 unit receiver, put it out there, it lost log. Not only the loss log, all the other receivers, they lost log. That's because the ionosphere was having disturbances. And then you can also see all the red lines. These are indications of the so-called carrier to noise ratio. It's an indication of how strong or how weak the signal is. You can see the signal, normally a GPS signal is about 45 dB. And when the ionosphere was disturbing it, would drop down to 10, 15. And so the commercial receiver, the high-end receiver, was having trouble. But then you see the red lines. The red lines are the algorithm we developed to allow us to sail through this period. And we can capture the signals. And that allow us to obtain information about how strong the ionosphere turbulence was, how it was disturbed. And so I always make this statement. I said, there are thousands, 10,000 receivers around the world that are used to monitor ionosphere. They will stop working when the ionospheres really need to be monitored because those receivers are not designed to handle the kind of stress So I wanted to build a receiver to handle those stress. And I'm translating those technology to spaceborne receivers so they can handle signals that are received by receivers like the ones on Triton. Reflection signals are even weaker, and they have a further interaction with Earth's surface. They have additional absorption. They travel additional distance because they have to enter the ionosphere, troposphere, bounce back, travel through them the second time. So their signal is even weaker than this. And what I wanted to do is bring the technology we have developed over the last 2 decades to work with spaceborne platforms. And that's what I've been working on the last 5 years. So I will just give you a quick overview of this background. So in terms of worldwide GNSS monitoring, we have built up a lot of systems. These are the stations we have around the world. They're strategically placed so we can monitor the ionosphere over equatorial areas, which you see Taiwan is right there. And in fact, we have a station there. And Lauren Chen is hosting a station for us that we're collecting ionospheric disturbance information there. We have a lot more stations over high latitude and over the southern hemisphere as well. I'm in Australia now because we're looking at perhaps extending some of our coverage towards that area. So, but I wanted to highlight one station that's in Hawaii, on Maui, on the summit of Haleakala, which is about 10,023 feet tall, over 3,000 meters. And this was how I got funded. I drew this diagram to our sponsors. I said, I would like to put a high gain antenna there. And I wanted to be over a cliff so that signals coming from rising and setting GNSS satellite could propagate through very thick layers of water vapors over the troposphere. And of course, perhaps they would also bounce over the ocean as well. But I want to have a high gain antenna so that I can really amplify the signal, bring it above the noise floor, and also without ground clutter, because I want to emulate that the platform on the CubeSat. Because on the CubeSat, you don't have ground below you to have ground clutters. And of course, I can have big computers to do on-site processing. And that allows me to study the planetary boundary layer and also study ionosphere if I could look southwards towards equatorial areas. And so we established this station in 2015, and it's been operating since then. So here are some actual pictures. We have this high gain antenna, 20-meter antenna. We have some zenith pointing antenna that emulating precise orbit determination antenna. So this dish is steerable. It's automatically programmed to steer towards satellites that's rising or setting over horizon. It's really emulating a radio occultation system, except that I have all of these powerful amplifications and support that a typical satellite wouldn't have. And the area we're looking at is in this diagram, and it's mainly focused on the southwest direction where there's no obstructed viewing areas. And here is some additional pictures. And to the right of this antenna is a building. That's where all of my electronics are housed. There's additional smaller antenna that has about 7 dB gain, have a second upward looking antenna. So I have a multiple backup systems. And by the way, this system is currently under expansion. It's adding capabilities to look at other signals other than GNSS. We're actually eventually into UHF, VHF, L-band, S-band, C-band, Ku-band, and X-band. So all of those capabilities are currently being updated so that I can look at other LEO signals transmitted from LEO satellites to look at their atmospheric and ionospheric effect. And we have other data sources that we work with. You're all familiar with Cygnus. I won't spend time about it. But SPY Global, GeoOptics, and Planet IQ, those are commercial small satellites. All of them are designed for radio occultation, but the SPY Global were collecting the so-called grazing angle reflectometry data, which I was the first scientist in the US that the NASA giving the data to do assessment in 2019. And the GeoOptics is kind of, I want to talk about it, but the Planet IQ recently started gathering reflectometry data. So we are already on contract to look at their data. And of course, everybody's familiar with Cosmic and Cosmic 2. Again, Taiwan played such a critical role in making this constellation operational, but it's mostly for radio occultation. And another satellite I would like to mention is the NOAA weather satellite. We've been working with it recently. It transmits VHF signals, and they take weather pictures and transmit down to the ground, really for weather purposes. But to us, the signals that's transmitted from NOAA 19 is a signals of opportunity, and we use those signals to study atmospheric effect. We've been collecting them over Alaska. I probably don't have time to talk about it today, but there are other things we work with. For example, recently, we have just delivered software-defined radio instruments to the Navy, to ONR, where we have radio frequency front end that can collect signals from 7 antennas mounted on aircraft, looking above, below, left, right, and front and back. And we have also developed UAVs that allow us to look at the reflectometry from a UAV over rivers and lakes. So that was a master's degree student project that has been completed a year ago, and we are about to start collecting data. And I put a Triton here. I'm hoping in my next talk, I could squeeze these aircraft UAVs into smaller pictures that I can put a Triton picture here to proudly let people know that we're working with it. Before I dive into reflectometry, I just want to give a little bit of background on ionosphere monitoring, because I think reflectometry, one of the biggest applications, I think one of the most exciting applications is ionosphere, and very few people have looked into that. So I wanted to play a little bit of emphasis on the background there. And just in case some of you are not ionosphere specialists, I want to give you a little bit of background to distinguish the different kind of ionosphere effects and what we're looking at. So the ionosphere effect, broadly speaking, there are two kinds. There's so-called refraction and diffraction. So let's say this is the ionosphere and the radio wave propagating through it. And so in a peaceful, quiet ionosphere, the plasma itself has ions and electrons, and the radio wave will bump into them. So the number of electrons it's going to bump into through the entire propagation ray path is called the total electron content. And you can imagine, if you're traveling from, let's say, New York City, from one end to another, if there's nobody on the street, you'll walk a little faster. But if there are a lot of people there, you're going to bump into people, it's going to be slow. The same thing is true with the GPS signals. So the refractive effect is really the signals got bumped into all these electrons. It becomes slowed down in its propagation speed. And because when we calculated the GPS signals range measurement, we assumed it was propagating with speed of light. So we actually would treat the range as if it took shorter time. And as a result, there's a range error. That error is proportional to the total electron content. The more electrons there are, the bigger the error is going to be. And this error is inversely proportional to the square frequency. So that is why GPS receivers or GPS satellites will transmit 2 frequencies at least. Because with 2 frequencies, we can see how the range errors are determined by those frequencies. As a result, from there, we can calculate how much TC is. The relative difference between the 2 ranges allow us to compute what is total electron content. So that is error that I'm not too worried about, because almost all GNSS constellations transmit at least 2 frequencies now, and we can correct for it. The problem is the diffraction effect. In the diffraction effect, is ionosphere have plasma bubbles or other structures. When that happened, radio waves hit it, will be scattered. When it got scattered, it won't propagate in a straight line anymore. So it goes through this kind of zigzagging through the ionosphere. When it emerged from below the ionosphere, you can think of this plane wave front is not uniform anymore, because each ray will travel the different distance. So this is so-called a phase screen. A phase screen is really, the phase distributions over this dimension when there should have been a uniform value, which is not now. And of course, the plasma will move, their turbulence. So these phase screens continuously changing. And of course, satellite moves as well. You're scanning different part of the ionosphere. And so when these rays travel further down to the ground, when they add together, there will be constructive and destructive interference. So what you're going to see is not a uniform ray pattern anymore. That's diffraction, and we also call them scintillation. So I'm showing you a couple examples here. On the top is the signal scale to noise ratio. And you will see all this disturbance fading, 20, 30 dB, and the receiver is under stress, like the example I showed you earlier. But in addition to that, it will also disturb the range measurement. On below is a range measurement disturbance. You can see all of these arrows in the range, which will cause errors. But the problem is more serious. When I can measure these errors, I'm actually in good shape. But quite often, when the signal is going through fading like this, receiver lose log. You don't have measurement anymore. So that is more damaging effect. And this cannot be mitigated by dual frequency. So it's the second part of this kind of effect, diffraction or scintillation, that is more damaging. I believe Triton can play an important role in observing this type of effect. And also, TC is another problem in the sense that without the TC, we don't understand the background ionosphere. And there are a lot of places on the Earth's surface we don't have TC measurement. And I believe that's another area reflectometry can play a role in there. So anyway, that is really what I wanted to show you in this next slide. So in the next slides, what I'm showing you are two maps. These are two maps that are built based on ground-based GNSS receiver networks. One was over in 2015, March 17, another was on September 8th of 2017. There were geomagnetic storms happening. And so these maps are so-called royalty maps. What it really did is it captured the disturbances in the ionosphere. So the harder colors are where there are a lot of disturbances. As you can see, lots of high latitude. But if you pay attention, watch these videos, you'll notice Taiwan is an area, and over the so-called ionization crest anomalies, that area we often also see disturbances like this. So the equatorial and high latitude are the areas that's most highly impacted. But as you can see in these maps, near the latitude over continental US, we sometimes also experience those effects, especially on September 7th and 8th, 2017, when this storm happened. Most of the US continental US was impacted, as you can see, coming down here all the way down to Central and South America. So this type of effect is very impactful for all sorts of applications. But one thing I really want you to focus on is looking at where their data. The data is mostly over North America, Europe, Australia, New Zealand, a little bit over Japan, and Taiwan. You should be very proud of you because there's data coverage there. But most other places, and things like Africa, South Russia, and even mainland China, because they don't share data, we have very little coverage. And the polar areas over Antarctica, there's very little coverage there. And over the vast amount of ocean, we have no coverage. This is where I think not only radio occultation can play a role, reflectometry can also play a role in here. So we've done some work in the past, but I'm going to skip this. And I will just briefly mention, we spend a lot of time doing machine learning. But when we do machine learning is built upon data science. And look at where the data come from. Yes, measurement in space and measurement based on ground, maybe forecasted models, but the real data, what we're showing here, again, it's showing that map I was showing you earlier. Most of the Earth's surface is not covered with them. And cosmic can cover some part of it over equatorial area, but not the rest of the poles. That's where reflectometry comes into play. These lines are from SPY Global's data over North Pole and the South Pole. And if Triton can fill some of the data gap, that'd be great. And here's the image of showing with our effort trying to do forecasting. And this forecasting is based on data coming from 1 hour before. And we cannot forecast any further. One of the big obstacles is the lack of data. So I think I'm, preaching to the choirs. But it's more than just space weather that we are worried about. one of the projects I would like to highlight here is called Meteor Tsunami Early Warning. Taiwan in particular is an area where meteor tsunami will impact you. It's a really meteorologically induced tsunami. There's earthquake-induced tsunami. Everybody's familiar with that. I want to talk about it. But the meteorological induced tsunami is less talked about, but it happens more frequently. So this is a paper that was led by my student from Charles Lin's lab, Chen Pingxuan. So he presented it a little over a year ago, but we are continually working on this project, and there are new developments that I would like to share with you later. But I just want to share with you about a part of this project. For example, in this area, if you see this green triangle, it's an area that's measuring air pressure. So this air pressure happened on this particular day, and you notice at 20 hours, 27 minutes, the air pressure starts having more fluctuations. But nearby, there's also a station that's measuring surface height. It's a buoy. So the surface height normally is measuring less than 10 centimeters fluctuation, but about 2 hours after the air pressure sensors, measurements are showing fluctuations, it starts having bigger waves that's reaching several tens of centimeters. So there's 2 hours of delay between these two sensors measurements. But there are also several TEC GPS receivers measuring TEC. And so you notice the TEC measurement starts showing fluctuations 14 minutes after the air pressure sensor. I only show the two stations here. I could show more, but it will clutter my screen here. So the GPS TEC's response to the air pressure fluctuation was quite timely. It's a 14 minutes delay compared to a buoy's measurement that monitor the waves driven by the ocean surface waters. That's much more slow propagation. That's 2 hours delay. So using GPS measurement, you can imagine we could provide early warnings when a meteor tsunami is happening, because it causes a lot of socioeconomic damage as well, big waves hitting coastal areas. So that's one area that's not really about the space weather. And now your questions may be, how does that relate to reflectometry? Well, these GPS receivers are on land. If we have reflections over ocean surface, that could even further give us warnings about the kind of meteor tsunami that's originated from deep ocean. And this is an area applications I want to bring to your attention. And of course, you already know about this Tonga volcano eruptions, which is in the deep ocean. And the way most people are monitoring it, this is where Tonga eruption was located. And it took a few hours for the ground monitoring stations over New Zealand and over Australia to pick up the waves, as you can see now. And recently, my student Pingshuan, I think I have some slides there, but these waves were picked up by over Japan, 3 hours later, and also it was picked up by ground stations over California 10 hours later. But people are not talking about picking up the signals over the ocean. And one of my students, postdocs, have done some work about radio occultation, picking up signals. But the radio occultation's horizontal resolution is very poor. It'll be very difficult to pinpoint where that disturbance is if you rely on it to do early warning. But reflectometry could change that picture. In fact, we're writing a paper about how reflectometry is picking up signals, which I will share with you a little bit later. I would consider everything I talked so far. I kind of try to motivate people to think about where reflectometry could play a role. But now I'd like to focus on reflectometry a little bit more. And I know you all probably have background in reflectometry already, but I really want to distinguish two different types of research. So reflectometry is really about signals reflected over surface that are picked up by downward-looking antenna on the CubeSat. And most people are focused on the so-called delayed Doppler map. The delayed Doppler map is because the rays that traveled to a CubeSat antenna can go over a large area because the surface is rough. There are all sorts of different small facets, different orientations over the surface that will point the reflection signal into that antenna. This area is what we call the glistening zone. So because of that, each of the rays travel a different distance to your antenna. And so there's a range of delays instead of a single point, like signals entering the antenna on, on the top of the CubeSat. There should only be one ray because it's only one pass, but the reflection ray have a range. And each one of these rays will correspondingly have a different Doppler. So there's also a range of Dopplers. So because of that, we have the so-called delayed Doppler map from a reflection surface. And this delayed Doppler map tells us the surface properties. So this is, and this is, I'm going to show you an example. This is a sequence of delayed Doppler maps one of my students built from UK's TDS-1 satellite. So each of these delayed Doppler maps are looking very different. Some of them are fuzzy. Some of them are tight, points. These fuzzy signals are reflected from surface that's very rough. So there's a wider spread of the delay and the Doppler values. But these other dots that are really focused on a single point, those surfaces are very smooth. It's like a mirror. So there are very little reflections from the surrounding areas. And most of those are coming from a specular reflection. And if you have signals like this, now you could concentrate on this point and actually do a measurement of this reflection ray path range. If you know this range, you also know your direct line of sight range. You could actually measure the surface height. And that's what we call altimetry applications. So in my lab, we do both kind of research, but I think we're more known for the altimetry applications because it requires a receiver to work with this very weakly reflected signal and to retrieve the very precise range down to centimeter level accuracy. So that's something that we have an advantage because we know about the receiver signal processing of weak signals very well. So that's where my lab is more known for. But before I talk about that, I just wanted to bring something I think we all should be very proud of is a student from Taiwan, Chen Pingxuan, did this project. So I'm showing you 4 maps here, and these are maps of the ocean wind and derived from Cygnus mission. And for September 14th, 2018, there was a typhoon that was hitting Taiwan in this area, right here where you see the hot colors where the wind speed was very high. So this map is from ECMWF based on real analysis using data from after the event and to construct this kind of map, used all sorts of sensor measurement and models. But on the right is a map that was constructed by Chen Pingxuan. He used a machine learning algorithm called bagged tree and used the signal measurements only. And this is the map he was able to derive from the delayed Doppler map values. And he was able to also predict the high wind near Taiwan area. And so you compare these 2 maps, you can see he captured most of the important features over the oceans and using reflectometry measurement. And in comparison, on the bottom, these are the Cygnus wind speed product. So on the left is a Cygnus version 2.1 wind speed product. On the right is a version 3. And clearly, its version 3 was much more improved compared to version 2. But if compared to ECMWF, I think Chen Pingxuan was doing a much better job using his machine learning algorithms. And I think when he finished his PhD with me, I think his ambition is to return to Taiwan to continue to contribute on reflectometry applications. And this is one area I think there's a lot of futures. But this is based on scatterometry measurement. And I think machine learning has a huge play in this future in terms of improving precision, resolution, and also in timelessness. And this is a comparison of the SFMR, which are sensor measurement of wind speed, including buoys and all that, as well as the Pingxuan's predicted wind speed. As you can see, they pretty much fall in the same line. I think the most outstanding contribution here is this is a H here. HW is high wind, and the BT is a backed tree. So Pingxuan was able to retrieve high wind. You look at the wind speed regime above 20 meters per second. This is where everyone else fell. And Pingxuan's algorithm was able to do that. And I'm really proud of him. But I wanted to focus a little bit more on the altimetry applications from here on. So the altimetry applications, its premises is that reflection signal had to be coherent. And so the coherency concept is defined like this. If you have a signal that's reflected over smooth, highly reflective surface like water, the signal is much more coherent in the sense that we could have the carrier phase measurements. Now, if it is over rugged land, most likely the signals can be non-coherent. People use those kind of information to do soil moisture type of applications, but I'm more interested in the coherent reflections. There are many, many applications for that. And so, and the way we can identify if a signal is coherent or not is if you see, let's say this ground track over a lake, and we color code it. The blue color here are the signals returns that we judge as not coherent. The red colors are coherent because this is indicator that we derive. We call them circular length. I don't have time to get into details how to get that, but this is a time series of these tracks. And over about 2 minutes of data. So this coherency indicator is telling me some areas are highly coherent, like in this red area, other areas are not. So by identifying this kind of segment of data, we could map lakes boundaries, river boundaries, and all areas that has high water content. So in fact, that was one of the projects one of my postdocs did. And he used the tracks, reflection tracks, and over lakes to identify where the lake boundaries are. And as you can see, this particular lake has very complex boundaries. But there's so many reflection tracks from Cygnus and from a SPY Global satellite. And he was able to build a mask or gridded lake surface boundaries map. And in fact, he worked with over 2,000 lakes. He mapped over 2,000 lakes and compared the accuracy of its boundaries with this so-called water explorers surface water database. And the errors or the differences between his map and the surface explorers database. And if you look at this horizontal axis here, these are the differences or the distance between his boundaries and the database boundaries. And you can see most of those distances are within a few hundred, 100, 200, 300 meters. Those are the ones with higher probabilities. And by the way, that difference does not mean his measurement has an error. It could be because the database was in average values because these lakes' water levels change, their boundaries change. So one of the great advantages of GNSS reflectometry is we could use GNSS reflectometry to monitor short-term variations, seasonal variations, in addition to long-term trend. So this is one area of work that I think will have high impact. And another area that we're very proud of is mapping river surface gradient. Rivers flow because water level is not uniform. Unlike lakes, now by the way, lakes are not uniform either, but they're relatively flat. But over rivers, the slope gradient determines the water flow. There are over 200,000 rivers on the surface of Earth. Most of them is not accessible by humans, but the water level flow, the gradient, it is important indicator of the entire global ecosystem because fresh water is drinking water and it's one of the most precious resources on the surface of Earth. So this is an example where we have reflection signal tracks from Cygnus. When every time it cuts across the river, you notice it's green shaded area, we see a very clear signature of slope. This average slope is about 4.5 centimeter per kilometer. We can get down to better than 1 centimeter per kilometer of river slope monitoring. And by the way, we have already mapped the Amazon River and Amazon River. And so Mississippi River and Amazon River in South America. And so I think there are many rivers in Taiwan as well and elsewhere in the world that mapping them is a very challenging task. GNSS reflectometry could play such a huge role in it, can monitor flooding, for example. And things like that, it's difficult to send people there to do measurements. And we've mapped the Gulf of Mexico. So this is the Florida here. And the Gulf of Mexico have an interesting phenomenon called loop current. So the background color shows the loop current during this week in August of 2020. For example, there's a high peak wave, 60 centimeters peak, right next to a 60 centimeters valley here. So this is over a meter of wave there. It's a standing wave. It can last for weeks. And these kind of waves are very important physical oceanography phenomenon. For example, if you have a hurricane coming in, and this kind of a standing wave magnitude determines how much flooding you're going to experience. So when there was a very big hurricane that flooded New Orleans for a long time, that was because Gulf of Mexico's loop current was very strong right around the time the hurricane happened. So in this figure, you show these tracks. These are reflection tracks from SPY Global measurements. And so what we did is we retrieved the surface height variations along these tracks. On the right are some examples. So the green lines are the graded sea surface anomaly models, which is the background color that I show there. They're very smooth because models are smooth. The black lines is what the tracks over the same areas, exact the same tracks over these graded lines, what we can retrieve. As you can see, most of the trends agree with each other, but our measurements has more fluctuations. But I think our measurements is more realistic because models tends to be more smooth. So, so this work has been recently published. And these slides, we have not published yet. It's brand new, but I want to share with you here today to show how powerful the altimetry measurement can be. This is the Indonesian Sea. It's not that far from Taiwan, but Indonesian Sea is a very, very calm area. There are a lot of dense tracks. These are all from SPY Global tracks. And the different colors represent different days from 2022. So there was a series of days one of my postdocs was looking at. So you can see over this week, there's so many tracks in this area. So she was able to calculate the surface height variations along these tracks. This is one small area that the surface height variation she was calculating corresponding to these different days of tracks. You could see the ocean waves in this area. So these are the tracks. On the bottom, she had built the topography based on these tracks. And this is a NASA-funded project. NASA was so impressed with this. We haven't had the time to publish yet, but I just want to show you the capabilities. And then we can also monitor interference from space. This is actually from Cygnus data, but we've also processed 1 year of SPY Global's data to monitor radio frequency interference. These are all done through machine learning because we have to distinguish what kind of disturbances on the signals are actually radio frequency, or is from ionosphere, or is it because the surface is rough. And they all have different signatures. So we have to process a lot of data, understanding all these other signatures in order to isolate these factors. So that is why earlier I said the ionosphere, the troposphere, the surface conditions, radio frequency interference, they all go in hand in hand. You can't be an isolated specialist. And you probably, as I was talking, you probably noticed sometimes these areas around the star have a big explosion of interference. That's because in North Africa over Libya, there was a major civil war going on at the time of this measurement was happening. So, so one of those things, this is also very recent, we haven't published either, is mapping land ice. So this is a map over Antarctica. These are reflection tracks over 1 day on October 2nd, 2021. So the dark areas are areas where the reflection signal have a very strong signal to noise ratio, meaning that the reflection is very coherent. In fact, this area is a so-called Ross ice shelf. And so this area of ice is known to be more smooth. And in fact, this map is data that are accumulated over the entire year of 2021. Because the ice doesn't change that fast, so accumulated data, the brighter areas shows the surface are more smooth. And we saw all these interesting patterns. And we amplify these patterns. These are very interesting because there were small islands in these areas. Those areas have geological deformations over Antarctica. And we didn't know what it was until we looked at a map from a paper published in 2021. These are a whole bunch of people studying glaciers, rock deformations. They used all sorts of sensors and models. They built this map, and this map is very similar to what we observed from GNSS reflectometry. So when we shared this with the people who wrote the papers, they were absolutely fascinated by it. They could not believe that GPS signals reflected from Antarctic can allow us to see something like this. And finally, I know we have a meteorologist, atmospheric scientist here. Reflectometry is a powerful way to map water vapor, especially over areas like Antarctic and Arctic, where it's very difficult to deploy sensors. For example, this is over Arctic Ocean. And this map is from, I think, ECMWF models, from real analysis. There's a plume of water vapor over here in that area on May 12, 2021. There were 2 GNSS reflection tracks from SPY Globals over there. They were separated by 3 minutes, not even 3 minutes, 2 minutes. And they both cut across these plumes. So what we did is we retrieved the surface height from reflection measurement. But we also have a good model of the Arctic Ocean's surface measurement. Those are from dedicated satellite altimetry measurement like ISAT. So we use those measurements, treat them as a truth. Then we look at the difference between our retrieval and their measurements. And the difference we attributed to troposphere effect that we didn't mitigate. And this is what we derived. On the right-hand side, the 2 satellite tracks, the 2 atmospheric zenith wet delay, which is related to water vapor content. And that orange line, the gold line, is from model derived from the VMF3 based grid model. As you can see, we have agreement in trend, but we show a lot more detailed structures compared to the VMF3 grid. And because VMF3 is a model after all, they may not even have much sensor measurement in this area, but we could see all the detailed distributions of the wet delay along this path. And we just got funded by NASA to continue pursue on this project. And hopefully next time I talk to you, I have a lot more result to report to you. I mentioned earlier, ionosphere. To me, it's probably one of the most exciting applications for reflectometry. That's because reflection signals bounced off over polar ice area received by CubeSat is so strong. And with dual frequency, we can calculate total electron content. I understand Triton only have a single frequency, but with single frequency, we could monitor scintillation. I mentioned earlier, scintillation is more damaging factors in the ionosphere effect. So I think I'm really looking forward to that part of research. And I always share with people what we can do with dual frequency to map the ionosphere total electron content. This is an example that I always share with people because I'm just so proud of it. This is a track over Carol Sea, part of the Arctic Ocean. And the ray entered the ionosphere near the pole, exited above Siberia. So the total electron content along these 2 passes are shown here in the red curves. And the black line is the global ionosphere map, TEC map, along these passes. As you can see, the trend matches, but we see a lot more fluctuations, which captures more realistically what is happening over the polar ionosphere of all those disturbances. And if we analyze individual carrier phase measurement, we could look at the scintillation indicators. So, which we have done that as well, but I'm running out of time. So one of the reasons reflectometry is so important for ionosphere is because there's no other way to do it. For example, I'm showing here over the North Pole, the blue colors represent the Arctic Ocean, and the black dots are where we have GNSS receivers. There's nothing over Arctic Ocean. These black dots here are not receivers. These are markers, okay? So even if we have receivers here, there's also a problem because GNSS satellites, their orbit have inclination that prevent them reaching the pole. So this is orbit ground tracks over 24 hours for all GNSS constellations. And the GLONASS have a higher orbit inclination. It's in orange color. They could not reach the Arctic, circle either. So basically, even if somebody could put a GNSS receiver over here, they cannot observe the sky over them because there's no signal. But if you have a reflection satellite picking up reflections flying over here, the reflection path will come out over in the pole area, like what I showed you in the last example. So that is why reflectometry is such an important tool for ionosphere measurements. And so my last slide is just to summarize, the receiver technology we develop to allow people to improve, CubeSat orbit determinations, to improve reflection signal measurements, to improve even radio occultation satellites. And the ground measurements are always needed when you try to validate reflectometry radio occultation measurements. So we also need robust technology over there. So this just summarizes the technology we develop in all domains actually would work hand in hand to support the next generation of Earth observation applications. And so that's pretty much the end of it. And I just wanted to make sure people understand I didn't do all that work. I'm the head of the lab. These are the people working with me during the last few years who had contributed to the work that I shared with you. Students, postdocs, they're the real hero behind all this. And all my collaborators, both internally, externally, the people host my stations that allow me to collect raw data, develop technology, and my sponsors. So thank you.
Thank you very much. Thank you for Professor Morton for this wonderful talk. It's amazing. And so let's save the time for students or the participants. Any questions?
I think sometimes people can be very shy. And
I know.
I'm going to put my picture up here so that people can see that I'm just ordinary person, not even in suit. I'm just in t-shirt here. And so there's no stupid questions, okay? So anything you ask, I'll be happy to answer. I know it took me a little bit longer to get to here, but I have time and I'll be happy to stay for as long as it takes.
I think we have many students here. So usually students are quite shy. So maybe let me just maybe start a few questions for discussion. Yeah. So since I'm meteorologist scientist, so I would like to focus more on the atmospheric application. So, but I'm very surprised and amazed that the reflectometry actually can do also water vapor retrieval. That's really amazing, and that's also additional the value. So it's really exciting. So my question is that so to retrieve the ZWD, so we need to first I should say calculate or estimate the surface height in order to convert to the So
yes.
Okay, may I ask so how to is there any, for example, in terms of the accuracy or uncertainty of this? Because if we have ZWD, then it can be easily converted to precipitable water.
Absolutely, yes. We have already done that too. Yes, absolutely, yes. Yeah, the conversion from wet zenith delay to atmospheric water vapor content, that's a straightforward calculation. It's a scaling, basically. Yeah, so that's pretty easy. So the really challenging part of it is to calculate the surface height. So in this diagram, you can almost see how we calculate it. You know this straight line of sight, and you know this reflection ray length. Okay, actually, the most challenging part is retrieve this ray distance. And the difference between this distance is actually proportional to the height of the satellite. And it's really that height divided by the sine of this elevation angle of the signal. But we know this height, we know the antenna height. So it's a height difference between the antenna and the ground. Because we have upward looking antenna, that gives us precise orbit. So we can if we can calculate the height difference between the antenna and the surface, and we know that antenna height, then we can know our surface height. So that's how we get it. But you're absolutely right about there are a lot of error factors. One of them is ionosphere, because the ionosphere is error factor here. But if we have dual frequency, we can mitigate that ionosphere height. And there's orbit errors. GPS satellite orbit, we can get a precise orbit from IGS. And the receiver, we have to have precise orbit. I do not know what kind of Triton's orbit accuracy is, but Spy Global's orbit wasn't that great. But once we have some of the onboard orbit data, we can further process it. So we could get down to 10 centimeter accuracy with the Spy Global's orbit accuracy. And so those are some of the major things. Another important error is actually the satellite clock. The CubeSat clock has errors, and that error can be computed again using the upper-looking antenna based on overhead satellite, which the signal is clear, and that allow us to give any estimation of that clock error. So once we know all those errors, what's left is a troposphere error. And it's important that we use very low elevation satellite, because whatever troposphere error has got amplified at the low elevation. You can imagine if you have a zenith delay, vertical zenith delay, whatever you call it, let's call it D, and then if your satellite elevation is low, you have to multiply by the mapping factor. The lower the elevation, the larger the mapping factor, the larger the troposphere contribution. So we've done some calculation. If you have a 5 centimeter of a zenith delay, wet delay, and at a 5-degree elevation, it's a 68 centimeter. So it's a huge amplification factor. That is why we can retrieve the troposphere very nicely.
Okay. Yeah. That's very exciting. So, so one more question is that because in your application you particularly apply that to the Arctic regions, and so for this kind of retrieval, is there, for example, we know that there is a lot of water vapor coming from tropic and subtropics. So, is there should we expect that we will also share the same accuracy for this kind of vapor retrieval?
I love your questions. We will really work on that. Yes, because the tropical oceans are very calm. As long as, remember, if we can do, so in these slides, I showed we can retrieve wave height like this. As long as we can retrieve surface height, then we can do it. And the tropical oceans itself, because it's relatively calm, relatively flat, and whatever wave surface height change you see here, these are in a few tens of centimeters. The troposphere error, especially if there's a lot of water vapor, we're talking about the tens of meters of errors in there. Yes, we can do that. In fact, we have already done that. I haven't shared it here because we haven't published yet. The number one, number two, we need to do validation. We have not been able to do validation yet because we've been working around the clock on this. And but the answer to your question is yes.
That would be wonderful. Yeah. So, okay. So, do we have questions from students? Not yet, but that's okay because I have tons of questions. So maybe I can, encourage students to engage to our discussion. So I have 2 more questions. The first one is about the river slope. That one is amazing. So, like in Taiwan, we also have a lot of rivers, but very steep. And that also cause a lot of when heavy rainfall, it's very dangerous for the disaster. So so for this kind of technique, is there any kind of, for example, limitation for the slope? So
this is an excellent question. So yes, there are limitations. If the river is narrow, remember when we are doing this kind of retrieval, the reflection signal have to have certain footprint. It's a so-called Fresnel zone. So for carrier phase measurement, the Fresnel zone depending on which direction you're talking about, along the track, that is determined by your elevation. So if at a higher elevation angle, the footprint is smaller, but even a smaller footprint, we're talking about 500 meters to a kilometer. Across the track, it's about a 500-meter radius. So that means that you are actually receiving signals coming from within that 500 meters footprint. So if your river is only 100 meters wide, that means you're taking 400 meters of data from the bank, river bank. When that happens, you are going to have a lot of non-coherent scattering entering your antenna. So your signal to noise ratio will be very low. If your signal to noise ratio is low, your retrieval precision is going to be low. So there's a river height issue. And we've done some analysis. And based on our experience working with, because we've worked with hundreds of rivers already, if the river width is less than 200 meters, the signal starts looking very corrupted. And the bigger than 200 meters, the quality is good enough. And of course, for bigger rivers, it's not a problem. So yes, that's one major limitation is it cannot work with very narrow rivers. But if in Taiwan, those rivers is along tropical rainforest, your ground is wet, that will become a lesser problem because your wet ground, actually, its contribution is not so non-coherent. We have processed data over Bolivia, over rainforest. We can see the signal very clear. Even when there's no river, the ground was very clear. So depending on where the river, to answer your question, basically, if the river is along a desert and stuff like that, anything below 200 meters in width, we're not going to be able to detect it. But if it's a river wider than 200 meters, we can see clear signature. If the river is narrow, but in tropical rainforest where the ground is wet, then we can still see them pretty well. Yeah. So that's basically, that's an excellent question. That's something that we're trying to quantify it at this moment. That's part of our project.
Okay. Yeah. Thank you very much. Thank you. And okay, so I have one more question about so not only for the I see this technology not only for the spaceborne, also for ground-based. So I saw that you have this collaboration on this high mountain location in Hawaii. So I wonder, can you share some comments or suggestion that is that possible for Taiwan? Because we also have very high mountain, and it will be very helpful if this kind of technology can be implemented, and also we can observe the PPL structure nearby the Taiwan.
That's another great question. Actually, before I even answer that question, I would like to draw your attention to UAVs and aircraft. So if you have UAVs and aircraft, if you have reflectometry on those platforms, they're much closer to the Earth's surface. Their footprints are much smaller. For example, our UAV, we fly it around 700-meter altitude. It's a footprint now is meter. So if we have a reflectometry from a UAV, now we can detect river slope of rivers much narrow. Now we talk about meter or so. Okay, so I wanted to add to that. That's a project we're working on. As far as this Haleakala station, it's absolutely possible that you should be able to do that. And I'll be happy to help to share with my experience in setting up these stations. Our station wasn't set up overnight. And the first time I wanted to do it was, I believe was 2013. I was at the conference. It was the first Pacific PNT meeting there. And I went up to the mountain just for the sightseeing trip. And I had this idea to do it. And I started hitting people for money. And we made our first trip in 2015. At that time, we cannot do it permanently because this is a sacred land for the native Hawaiian people. They do not allow you to put something like that up there. And they will only allow you to put it up there temporarily for 2 weeks. And so during that 2 weeks, we collect a lot of data. And I didn't share any of the data with you today because I didn't have time. We had amazing data. And I used that data to come back to ask for more money. And I also was able to present our results in a way that people can understand, talk about the impact, how we can help monitor the environment around Hawaii to the native Hawaii tribes. And they were so impressed. So they give me special permit. And so we were able to go back in 2017 to set up a permanent station and continually to improve it. So you can imagine this was effort. This first happened 11 years ago. And so it takes time, but I will be happy to share my experience with you. If you're interested in some sites, you want to set it up, I'll be happy to provide any kind of technical insight that we have, and I won't hold anything back. Absolutely, you should be able to do that.
Okay, yeah, that's very impressive. Thank you. And actually, of course, I think that we will be very interested to know in all kinds of way to really improve or expand the application of art receiver, and so.
Yeah, the planetary boundary layer. Let me see if I could. I have another presentation that I have a picture that I can show you. Yeah, so this is a signal we picked up in Hawaii, and I don't know why I have all these weird symbols here. But anyway, so this is satellite that's rising from below horizon. In fact, you should be able to see. So you should be able to see, this is the elevation of the satellite here. So this satellite was almost 5 degrees below horizon. And by the time of this experiment, by the time the end of the experiment, it was about at the horizon. So we were picking up signal way below horizon, okay? The signal was bent, So the signal have very little power at first, and then it starts coming up. And at this kind of low signal to noise ratio, most receiver, no one else receiver can do it, but we could. By the time it was hitting horizon, it was stabilized about 40 dB hertz. People can do it. But the interesting thing is here, you see the signal to noise ratio was going up, but then went down. This is when they hit the planetary boundary layer. There's a troposphere duct there. And so by looking at the time when this is happening and the elevation angle of the signal, we can derive the planetary boundary layer height. So we actually published a paper only several years ago based on measurement from this area. And this is a very powerful technology. But the key here is your receiver has to be working here because the signal is really bad, okay?
Yeah.
All right.
That's really this is really excellent application because I mean so recently we have a lot of research and interested especially in the marine PPL, the structure, and we also identify that if the wind speed and also the PPL change in how that may change the moisture transport. So that's also linked to the heavy rainfall in Taiwan. So I believe that if we can expand this kind of study, that will be very beneficial for Taiwan. And also I would like to emphasize that in Taiwan, we also have very strong team that working on UAV observation, but that's mainly for the environment. So so I guess like people will ask that for this kind of, for example, UAV so in terms of the size, is there any kind of requirement for?
I'll be happy to share those information. I have a UAV in the lab, and we have finished implementation on that. And it's yes, we already done flight test and all that. I'll be happy to share those detailed information.
I guess we will need the like another talk, another seminar. But thank you. And may I ask, like, students or any participants, do you have questions? I think
But your questions are all excellent, and thank you.
Thank you. Thank you very much. This is really.
I wish I knew you better before I went to Taiwan, because I didn't know you, and
I'm sorry, it's my fault. I should introduce.
No, it's not your fault, and I think. But you know, it's never too late. So I can see many different opportunities that we can collaborate.
Yeah, and especially we work very hard to try to apply the GNSS signals wind speed assimilation. So mainly my work is related to data assimilation. So we know the importance of all this the satellite data, remote sensing data, but we would like to bring in those data into the numerical modeling and prediction, so that we can really bring out the value of those data. Yeah. So I think the it's more than 1 hour. So I hope I can continue the discussing with you later. I mean, in later days. But first, let me. Again, I really appreciate this great opportunity that Professor Morton have given us to know all these wonderful applications. Yeah, Charles, do you want to say?
Thank you, Charles. Yeah. And Charles, I know you have a couple of students you would like to visit us in April, and we have to chat offline about the time. Okay.
Yeah. Okay. I'll do so.
Okay.
Thank you.
Thank you, Charles.
Excellent talk. Thank you.
Yes. So I think that I will stop here and let's thank Professor Morton again. And if you have any questions and want to know more about all this wonderful work, and please email her, and it's the great opportunity. Okay. Thank you.
Thank you. All right. You guys all have a good day. Okay. Well, thank you.
Thank you. Okay. Thank you all very much. Thank you.
Okay,
so
bye.
bye.
Yeah.